Hi everyone, welcome back. So for today's lesson, we will be learning about almost exact differential equation, which is similar with the exact differential equation that we've done in the previous video, but now we have an integrating factor to find. So without further ado, let's move on to our first example. Hi everyone, so this is our first example for today's almost exact differential equation. So we have here 4 times sine of y plus 6 over x times dx plus x times cosine of y times dy equals to 0. And we know in a matter of fact that this is in a general form of an exact differential equation. And now let's do our first step for an exact differential equation, which is checking whether it is an exact or non-exact. By taking the partial derivative of f here with respect to y, we will get 4 times cosine of y, and also taking the partial derivative of f with respect to x here, we will get cosine of y. And this shows us that my is not equal to nx, which this is a non-exact differential equation. But wait a minute, the difference, if you see here closely enough, the difference between my and nx are just slightly by a tiny bit. And so we can say that this is an almost exact differential equation that we can make it as an exact differential equation. By what? By using this formula here to find the integrating factor. And after we've got the integrating factor, we will multiply it by this whole equation here, or our original differential equation. And let's go and find the integrating factor, which mu x is equals to e to the integration of my. We know my is 4 cosine of y minus our nx is cosine of y over our nxy, which we know is x cosine of y times dx. And so we know that our numerator will be 3 times cosine of y. Our denominator will still be the same, x times cosine of y dx. And we know that we can cross out the cosine of y here, and this gives us e to the integration of 3 over x dx. And our integration 3 over x will gives us 3 ln x, which we can make it into e to the power of ln x to the third. And we can cross out the e and ln, and this just gives us x to the third as our integrating factor for this almost exact differential equation. And after we found the integrating factor here, let's multiply it with our original differential equation, and that will become 4x to the third sine of y plus 6 over x times x to the third is just 6x squared dx plus x times cosine y times x to the third is x to the fourth cosine of y dy equals to 0. And now let's check whether our differential equation that we've generated here is an exact or still a non-exact by taking the partial derivative of f with respect to y on the left hand side. That will gives us 4x to the third cosine of y, and on the right side let's take the partial derivative of f with respect to x. That gives us 4x to the third cosine of y. And we can draw our conclusion here that my is finally equal to nx And therefore, this is an exact differential equation, and we can solve for it. After this step, after we've solved for the almost exact and make it as an exact differential equation, we know that we just need to do the same steps like we did in the exact differential equation, which I will take here, the equation here, or actually the partial derivative of f with respect to x, f of x equals to 4x to the third times sine of y plus 6x squared. And now we're going to integrate it. Same steps, remember, like in the exact differential equation, the integration of 4x to the third sine of y plus 6x squared dx. And remember, in this integration process, what are our constants? Our constants are the y's. So we just need to integrate it towards the x. So 4x cubed times sine of y becomes x to the fourth sine of y plus 6x squared becomes 2x cubed plus h of y, or the generic function of y. And after we've got our f here, we're going to take the partial derivative of f, remember, with respect to y. And this gives us x to the fourth cosine of y plus hx and y, or the derivative of h. And we're going to set it equal with our partial derivative of f with respect to y here, with the partial derivative of f with respect to y that we've just got, and things will cross cancel out, and we can solve for our hy, and that will substitute it back to our equation that we got here. Okay, so x to the fourth cosine of y plus hx and of y equals to x to the fourth cosine of y. And we can see here that we can cross this x to the fourth and cosine of y, and our hx and of y will just become 0. And if we integrate it to solve for h of y, the integration of 0 dy is simply 0 plus c. And so substituting it back to here, our h of y, we will get x to the fourth sine of y plus 2x to the third plus, actually it's 0, so we don't need to write it, equals to c. And this is our final answer to this almost exact differential equation, or our general solution, since there is no initial value problem given at the start of the problem. Hey everyone, we are back with our second example for an almost exact differential equation. We've got here 3 times x squared plus y times dx plus y times x squared minus x times dy equals to 0. And in fact, we know that this is in the form of an exact differential equation. And now, let's do our first step for every exact differential equation, which is checking whether the my is equals to nx makes it exact or non-exact. First, taking the partial derivative of f with respect to y on the left-hand side gives us 1. And on the right-hand side, take the partial derivative of f with respect to x, which is equals to 2yx minus 1. And here we can see that my is not equal to nx, which this is a non-exact differential equation, or to be more precise, this is an almost exact differential equation. And how do we make this almost exact differential equation to be exact? we're going to use this formula here to find its integrating factor, and multiplying it after finding the integrating factor, we will multiply it with our original differential equation here. And so let's try to find our integrating factor, which is mu of x equals to e to the power of the integration. My is 1 minus 2yx minus 1. Minus times minus is positive, and over nxy, which is y x squared minus x dx. And if you're faced with an integration like this one, don't panic. Just simplify it and make it as the simplest form as you can make it. And so 1 plus 1 is 2, 2 minus 2yx, we can pull out all of the 2, and this will become 1 minus yx over. At the denominator, we can pull out all of the x's, which makes it x times y, x minus 1 dx. And from here on, we can see that 1 minus yx divided by yx minus 1 is just a multiplication of negative 1 or minus 1. And so we can cross this out, but we can add a negative 1 on the top, which makes this into the integration of negative 2 over x dx. And this will gives us e to the negative 2 ln x, and we can make it as e to the ln x to the power of negative 2. We can cross out the e and ln here and make this into x to the negative 2 or 1 over x squared. And we've got our integrating factor here. Now let's multiply it with our original differential equation, which is on the top here. Okay, so we're going to multiply everything with x to the negative 2, which 3x squared times x to the negative 2 is just 3, plus y x to the negative 2, close bracket, dx, plus yx to the yx squared times x to the negative 2 is just y, minus x to the negative 1. Now dy equals to 0. Now, after we've done until this step, let's check again the differential equation that we've generated here after multiplying the integrating factor with the original differential equation. So let's check and take the partial derivative of f with respect to y here. And this will simply gives us x to the negative 2. And let's take our partial derivative with respect to x on the right hand side. And this will gives us also x to the negative 2. And here we can draw our conclusion that after multiplying the integrating factor, my is equal to nx. Therefore, this is an exact differential equation that we can solve. And from here on, we just need to do the same steps like we've done in the exact differential equation, which we will take this equation here, the partial derivative of f with respect to x, xy equals to 3 plus y x to the power of negative 2, and we're going to take the integration of 3 plus y over x squared dx, and the integration of 3 is 3x plus the integration of y over x squared, or y times x to the negative 2, is just negative y over x plus h of y, or the generic function of y. And from here, we're gonna take the partial derivative of f that we've got with respect to y, which is fy equals to 3x becomes 0, negative y over x will become negative 1 over x, h of y will become hx and y, or the derivative of h. And after that, we're gonna set it our new partial derivative of f with respect to y here with our partial derivative of f with respect to y over here. And we're hoping that something will cross cancel with each other. So equals to y minus 1 over x. And we can see here that negative 1 over x and negative 1 over x can cancel with each other. And so let's cancel them out. And our h of hx and of y will become y. And now we're taking the integration to find h of y and substitute it back on the top here, which h of y is the integration of y dy, which this will be 1 over 2 y squared plus c. And now substituting it back to here, we will get 3x minus y over x plus 1 over 2 y squared equals to c. And this is our final answer, or the general solution for this non-exact or almost exact differential equation here.